So yeah, the third question from the Stats Step 3 Sport booklet. This is a very long question with an absolute ton of algebra to do in it, but we should be able to get through it eventually. So we've got letters A and B arranged in a row in a big long word just of A's and B's, with a bunch of A's and a bunch of B's, and nothing else. The word is just made of A's and B's. Anyway, we have that x1 is equal to 1 if the first letter is an A and 0 otherwise. And then for every other letter, like x2, x3, x4, and so on, that's equal to 1 if the kth value, so like if it's x4, then you need the fourth one to be A, and the one before that would need to be B. And then it would equal 1 and 0 otherwise. Now, it's important to note at this point, there is only like one word, I guess, going on here. So if you want more than one of these things to be true at the same time, then if you want x1 to be 1, then the first has to be A. And then if you also want x4 to equal 1, then the fourth has to be A and the third has to be at the same time as the first equals A. Like there's only one word here going on. Anyway, we have this random variable S, which is the sum of all these xi's. And by finding expressions, we can start doing some stuff. Okay, so let's do this. So firstly, if I equals 1, then, well, okay, we're only thinking about like x1, I guess. And the expected value of x1 is just 1 if the first letter, this is just me saying the first letter needs to be an A, and 0 if the first letter isn't an A. I could have written that in words, and I probably should have done, but I was being lazy, so I just wrote this. The probability the first letter is an A is just A over n, because there are A A's and n things in total. So the probability the first one is A is just A of n times by 1, and then the other thing is times by 0. So that's just the expected value of x1. Now, for the others, you need a couple of things to be true. You need, as we were saying before, you need the kth to be an A and the previous one to be a B. And it's going to be 0 if, and I've done some more lazy notation. This was just me writing down like it's 0 if anything other than this is happening, right? It's 1 if this is happening and 0 if anything other than this is happening. So okay, well, what's the probability of having B in the 1 minus ith position? Well, there are BBs and n things in total, so that's B over n. And then A in the ith position, well, there are now only n minus 1 things because you've already put a B here, but there are still AAs, so it's A over n minus 1. And if we just times these things together, that will be our probability of that happening, times by 1, which doesn't do anything, and then add 0, which also doesn't do anything, and we'll end up with this here. So okay, and now it says E of S, where S is the sum of all of these things. So E of S is just the sum of all of the expected values of all the things. Because, of course, just E of this, you just do all of these E's individually and then add them all up. So that's fine. Now that's going to be this, and then all the other ones are just this. And there are n minus 1 of them, right? Because it goes up to n, and there's one thing here that you're not counting, so all the other ones, there are n minus 1 of them. Cross those out, and then, of course, we can add these together and even do some factorizing, and we end up with the desired result. Now it starts to get a bit more complicated, I guess. For j bigger root of 3, this thing is this, apparently, we need to show. Now, if j is bigger root of 3, remember what I was saying before about if you want a combination of things to be true, then you need, if you want x1 to be true at the same time as x3, let's say, you need an A in the first letter to make this one 1. But you also need an A in the third letter and a B in the second, right? So this is actually fine, right? Because there's no overlap between these things. As long as j is indeed at least a couple of places above 1, there isn't any overlap or any contradiction between what you're aiming for here. So that's kind of fine. And of course, if either of these two conditions aren't 1, then when you multiply them together, you're going to get 0. So this is me writing that statement out, which is the expected value of this is it's 1 if they're both 1, 0 if this one's 0 and this one's 1, and so on. But none of this matters, right? So all I'm saying is I just need them both to be 1. And when I times by 1, because that's the value of it, it's not going to do anything, so I can get rid of that too. So I just need these things to be true. Now, I know what the probability of the first letter being A is. It's A over n. Now, what's the probability of the kth letter being A and the kth minus 1 being B? Well, the probability of the kth minus 1 being B is B over n minus 1, because there's only n minus 1 things left, because you've already put an A here, and there's still BBs left. And then when you want the other A to go in the kth letter, you've only got A minus 1 A's left and N minus 2 things in total. So we're going to times together all three of these things to get this here. And then, of course, times by 1 doesn't make a difference, and adding all the zeros also doesn't make a difference. So we'll end up with this here. So that's that one done as well. Now, part B is where it gets super tricky, and it starts to become very fiddly as well. So now we have this thing where we're timing these two things together, but this is no longer necessarily 1. Now, the good news is J is still a couple of places above it, apparently, so that's fine, because that means the interaction Like the problem is, and I'll say this more clearly as we're doing it, but like you can't, for example, the expected value of like x1, x2 is 0. X1 and x2 can't be 1 at the same time, because if x1 is 1, then that means the first letter is A. But if x2 is 1, then that means that the second letter is A and the first letter is B, and you've got a contradiction in the first letter. So the fact that these are separated out is a good thing, and is what we're going to have to sort of end up aiming for. If we first think about this, though, the expected value of this times this. Now, I've chopped off some working then. There should be a 1 here, and then there should be a plus a bunch of zeros. All I'm really saying here is that I want both of these things to be 1 as they were before here. Like it's the same idea. And to make this one 1, I need the first letter, so I need the ith letter to be A and the jth to be B. But for this to be 1, I need the ith, for xi to be 1, I need this letter, the ith letter to be A, and the ith minus 1th letter to be B. And then for this thing to be 1 as well, I need the jth letter to be A and the jth minus 1th to be B. Again, as long as there's no interaction between the I and j, as long as they're far enough apart, which I'm sort of hoping that they are. So when I sum these things up, again, I'm keeping this distance between them by saying, well, if I take it from I plus 2 is j, that means that, when I is 1, j is 3, and then when I is 2, j is 4, and we'll end up not having this interaction. They'll be spaced out just enough. Well, of course, we can just times all those things together, and then how many of these things are there that we're just adding up? Well, if you're going from 1 to n, there are n things. So it's almost like doing n minus 1, and then plus the 1 at the bottom. So to get the number of things between this and this, let's do this minus this, and then just plus a 1. That's probably a really stupid way of doing it, but it ends up being this many things, which is the correct number of things. So from 1 to n is n minus 1, and then just add 1 for the hell of it, because essentially you're trying to count the first thing. So for this, it's this minus this, and then just add a 1. So okay, we end up with this, and that's how many things multiples there are, and we end up with this as our sum for the first bit. Now we need to do this other sum. So we need to add these up from I equals 2 to n minus 1. So this sum here of these things. Now, notice that, we're running from I to n minus 2. Very little of this even has an I in it, right? So what we can do is we can say this term here is n minus 1 minus I, and then expand out to be n minus 1 times this thing minus I times this thing. Now, the n minus 1s cancel, but even better than that, we can separate the sum out into two different things. And now this doesn't have anything to do with I at all. This is just a number that's completely independent of the sum that's going on, I guess. So let's just pull it out to the front and just say there's a 1 there. And likewise here, just pull this out to the front and say that there's an I there, because there still is. Now the sum from the sum of 1 from n to n, so from 2 to n minus 2 is just how many things are here, which again is n minus 2 plus 1, which is n minus 3. And then this one's a bit more complicated. But what I said was the sum from 1 to n minus 2 is, just do the triangular sum thing. It's n into n minus 1 over 2. But n is n minus 2. So it's n minus 2. Sorry. The sum is from 1 to n. It's just n into n plus 1 over 2, isn't it? So if n is n minus 2, then it's n minus 2 into n minus 1 over 2. But we're missing the first term when I is 1. So just take away a 1 to get rid of that. And then if you combine these things together, it actually ends up factorizing nicely to be this. And like I said this earlier, was just n minus 2, take away 2 plus 1, which is this. Now these two things cancel, and there's some more cancelling over here. And eventually you end up, I think, if you put these things together by making a common denominator and factorizing out a bunch of stuff, I guess, because a bunch of stuff factorizes straight away, then put these things together, actually it ends up making one more piece of cancelling, and we end up with the desired result eventually. Which is what was required. So quite a lot to do there, and now we're into the final bit, which is, I said these bits were fiddly. This is the fiddliest bit, I think, for sure. The variance is defined to be this, E of s squared minus E of s all squared. Now we know E of s is here, and I can just square that, so that's not going to be a problem. Now E of s squared is going to be more of a problem. S squared is this times itself, and this, of course, is x1 plus x2 plus x3 all the way to n. I shouldn't have really put dot 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 because it's up to n, but I was being lazy. It's fine. So it's this times this. Now, when you multiply these out, you end up with x1 times x1 plus x2 times x2 plus x3 times x3. And then you have all the cross terms. And every single time you have a cross term, like x1 times x2 and x1 times x3, you'll have two of them, because you'll also have not only this x1 times x2, but this x2 times x1. So there'll be two of every single cross term, which I have lazily denoted again, without really denoting it at all. It's the cross terms that we need to think about kind of carefully. The easiest way to put this is obviously this is just the sum of xi from 1 to n. Like that's not complicated. So that's just this. So all of the same terms, just this. Now with the cross terms, the best thing to do is to say that you've got two lots of x1 times all of the others that aren't x1, plus two lots of x2 times all of the others that aren't x1 or x2, because you've already got the x1, x2 terms in here, and the x2 terms, of course, are in here, so it's just x3 and beyond. And then likewise, the next one would be 2x3 into x4 and beyond, and then 2x4 into x5 and beyond, and so on, all the way until the end. Now, a couple of things that are helpful here. As I've already said, x1, x2, or xn into xn plus 1 is always 0 because of the contradiction in one of the terms, right? So if n is, say, 10, then x10 is 1 if the 10th letter is A. Or I should be using this one, shouldn't I? And the 9th letter is B. But then x11 requires the 10th letter to be B, not A. So there's a contradiction there. Which means I can get rid of the first term from all of these brackets. I can get rid of this x2 and this x3 and so on, and just leave it like this. Now the next thing I can say is, well, okay, I can kind of write these as a sum within a sum, I think, in the sense that, well, okay, this sum here is just this, and then this sum here is just this, going from j is 3 to 4 to 5 to 6 to 7 and so on, all the way up to the top one. But then we've got a sum within here of just the xi of the 2, and then it's just x1, x2, x3, and so on, up to n minus 2. So it'll be a sum from I equals 1 to x minus 2 of the sum of all these things from the j's. And notice how the j's are helpfully 2 apart from the i's because of where they start, because of this. So like if you start at I equals 1, the j starts at 3, which is correct, and that's where it needs to be, up to n minus 2 because of this n minus 2. And yeah, like I said, this is very fiddly, but I think this just about works. And the reason this is perfect is because we have an expression for this thing, basically. It's like here, essentially. And we have an expression sorry, no, it's this one here, isn't it? Well, we definitely have an expression for this. That's all here. And this one is like here. It's perfect, almost, aside from this bit here. So that's a problem. Now this one here, I think we are going to deal with. Like it's not this one because the one we're about to use it in a second. But it should be fine. This one here. There's another trick to deal with this. Now this is almost perfect. I said it was perfect before because I'd forgotten one of the steps. But this is almost perfect. The I equals 1 is wrong. So that's fine. Let's just separate that back out. Essentially, go back to this line, and just don't put this term in the sum of the sum terms. Make it its own thing, right? Make it its own thing. Run from x1 to xj on its own, and then start the rest of them at 2. Now, the reason I want to do that is because it now makes this term perfect. It's exactly this. And this one here is found here, which is also perfect. Because now I can just apply expected value of everything, because I want the expected value of s squared. I don't really want s squared. I want the expected value of it. So we can do the expected value of all the things, which is perfect. Now, this one here is just this thing here, which is perfect. This, well, with the sum, but that's fine. We can just times by the sum. This thing here is literally just this thing here with a 2 here. I'll just times it by 2, and we should be all good to go. Now, this thing here, like xi can only take the value 1 or 0. So when you times it by itself together, you're still only 1 and 0. So this thing here is just the same as the expected value of xi. Like if it's 1, then it's 1, and if they're both 1, then it's 1, and if they're 0, then it's 0. So it's kind of just the same thing. So we can just say that this is just this. This is just the expected value of s. Those two things are going to be the same. It doesn't make a difference when you square xi, because squaring 1 is still 1, and squaring 0 is still 0. So the expected value of it is still going to be the same. This one here, like I said, we know this is this. The sum of it, well, how many terms are there? Well, there's n minus 3, and then add the 1 again at the end, as we were saying before, is n minus 2, and then there's 2 of those. And then this thing here is just perfectly this thing, but there's a 2 in front. So we have this. Do a bit of cancelling. There's some clever factorization we can do from these two terms. And like, you never want to do, you always want to factorize as early as possible, right? Because then otherwise you're just needlessly expanding only to try and factorize a harder thing later. So from these two terms, factorize out an a and an a minus 1. And a b actually as well from there and there, and then the rest of the terms left over are this 2 and this b minus 1, which we can just add together, and then this just becomes a b plus 1, which is helpful. Okay, and then Of course, I've also times this by n minus 1 over n minus 1 to put it in the same sum as the other two. Now we can finally consider the variance, which is that thing we just wrote down, minus this thing squared. And all we have to do is try and make this look like this, which, as long as we haven't made a mistake up to this point, it should just about eventually be. So I've squared this thing out. I'm going to times this thing by n minus 1 and times this thing by n over n. Again, I'm going to try and factorize as early as possible. So in this entire top row, a is in everything, and so is b plus 1. So we can take that out. That leaves behind this stuff. There's nothing in common, but it doesn't look that terrible. So I'm going to expand it out. This n squared is a concern because there are no n squareds anywhere else, and I do apparently have to get rid of it. And this is where we remember way back at the start, maybe the question is here, a plus b equals n is a super helpful thing that we need to remember here in order to make stuff go away. We've got an a and we've got a b somewhere, have we? These two terms cancel. I'm sorry, we've got a bn and an an. So when you factorize out that becomes minus bn into b plus a. That's this term and this term factorizing together. But b plus a is n, as we saw on the previous slide. So this is a minus n squared, which is fantastic, goes away with this. This can also be written as a plus b as well. And when we do that, then it cancels with this a, and we end up with this, which factorizes one last time into this, which is the result that we wanted. That was a super tough question, but yeah. The last of the step questions from the stats booklet is this one here, and we'll just get straight into it. So we can use this integral here, which is nice, and we'll do something with this. So this is random variable density function this, so therefore the integral between the domain of x, 0 to infinity, must equal 1, because, of course, if we imagine the area underneath the density function, its area must be 1, because probability adds to 1, right? So this is just what we can set up. Of course, we can remove the things that have nothing to do with x, because they're just constants, they're gone. And then we can use this result up here, because we can see that if a is m and n is 2a, then this is pretty much perfect. So we can sub those results into here, and still equals 1. Of course, we can do some simplification here, because this just makes a factorial. Could have written this as a factorial squared, but they apparently don't want us to in the answer. These k's will obviously cancel, all of those powers, and then we can just times and divide, and we'll end up with c as requested. Show by substitution that this equals this. Now, this is probably the hardest bit of this entire question, is figuring out what substitution you're supposed to use here to make this work. Like, the x's and the u's stay pretty much exactly where they should be. So it's tempting to use a substitution that looks a little something like, x equals u plus this thing here to try and force this 0 to become this. But it really doesn't work. What you need to realize is that you don't want this limit here to become this here. You want this limit here to become this one here, and likewise this one to become this one. And the way that we can make that work is we can use a substitution that looks like this, right? Because now if x was 0, u becomes k squared over 0, which is infinity, so that would be this limit here. Of course, it would be down here, but I can fix that later. And if x is v, then this becomes k squared over v, which is perfect, right? So at some point, we'll need to flip the limits over with a negative sign, but that's fine, because as soon as you differentiate this, you're going to get a negative sign. So that's great. So this seems like it might work. It's a hard substitution to come up with. I will mention that later on in the question, if you bothered to read through the whole thing, they actually ask you to do another integral, and the substitution looks a lot like this. So that could be one way that you figure out this is the one to use. Anyway, we can rearrange that for this. That's what's going to go into here. Of course, this makes minus k to the minus 2 x squared equal du equal dx. And we can replace all of that in there as well. Now, this minus is what we're going to use to flip these two limits over to the place where they should be. And we can also replace all these x's using this idea here, which I eventually did here, I believe. Eventually put them in. And now there's a bit of stuff to do here. It's not too difficult. Just times this by this, and this by this, and then this by, and then put these two bits together, I think is what I did. So I wrote this as k over u, so it's k squared plus ku over u. There's much easier ways to do this, by the way. But I kind of was just, it's just integration, right? Like it's just a bit of algebra to get through all this. When you got a quadruple stacked fraction like this one goes here and this one goes here. So it ends up like this, and then just a lot of stuff just cancels. Like this and this go together to cancel with all of this, so all the k's go away. And sorry, I should also say from here to here, I factorized out k from all 2a plus 2 amount numbers of these brackets here to make all of them there, and then replaced from there, which means these now will cancel. And of course, there's a bit of cancelling here with the u's as well, and we pretty much get to our answer as requested from there. So that's all good. Okay, excellent. Next one, deduce the median value of v as k. This is quite an interesting question here, because of course the median, as you usually write it, is the integral from 0 up to m is a half. Like that's the definition of the median, right? Where half the data is below and half the data is above, which means you can just as accurately write that the integral from m, where m is the median, to infinity is also a half. But of course, that means that this integral is equal to this integral, which isn't usually a useful thing to write down. But it is here because you see, of course, this is just a dummy variable, right? You could replace u's here with x's because that's just a dummy variable, right, in the definite integral. So, of course, that means that if these two things are the same, by this identity that we have here, that means that this m, for this m and this m to be equal here, we can have that m equals k squared over m. And therefore, when we times by m and the square root, we have m equals k, would be a suitable median, which is quite an interesting question, I guess. And then the expected value of v, of course, the expected value is the integral of x times the probability density function. So it's going to be x times this in an integral. So when you times this by x, you just end up with x to the a plus 1. And now actually, we can see again that all we're going to do here is use the same thing we did before, where this time m is a plus 1 and n is 2a, I guess, once we pull out all of the random constants that don't matter and replace the c with this thing here. Then we can use this, and we can put them in. We can put them into here using the things that I just said. And then lots of things cancel here, right? A plus 1 factorial over a factorial is just a plus 1. This makes a minus 1, which over a factorial is just an over a, because all of this is a times a minus 1 factorial, which is here, so it cancels. This and this, I think, just beautifully cancel with each other, except for one of the k's, I guess, at the top. And then this and this, of course, cancel. It all just works really well. And you end up with an expected value of v for that there. Okay, so we get into the home straight here. We've got quite a lot to go, I think, actually. The random variable v represents something, so that was what we just discussed. Then the time taken is another random variable, t, which is s over v. So we'll see here that that t and v are inversely proportional to each other. So if t is bigger or smaller, v is the opposite, it's smaller or bigger. So the critical value when t is equal to little t, v is s over t, which means if we want big T to be less than t because of the inverse proportion, that's very much the same as saying we want v to be bigger than s over t, because those two things are one and the same because of the inverse proportion and because the critical value t is equivalent to s over t for v. So therefore, p of v bigger than s over t, well, okay, by definition, that's going to be this integral here. The integral from s over t to infinity is the probability that v is bigger than s over t, which, as we said, is the same as p is less than or equal to t. So therefore, we can just replace this with p of t less than t, and we'll have this statement right here. Okay, so it's asked us to make this substitution, which is similar to the one we made earlier, to try and evaluate this integral here. So of course we can firstly throw in instead of x, we can write instead of x, because this is the same as x equals s over u, we can throw in s over u in replace of these. We can also differentiate this and then replace by dividing by s and times by x squared with a negative sign here. When we should also say that when x is infinity, u is 0, and when x is s over t, s over t is just t, so that's a t there. We can use this negative to flip these two signs over, or these two limits over, I should say. We can pull everything out that we don't really care about, as we did last time. Should there be an s here, or is this just me mistyping? I think this is me mistyping. Oh no, sorry, it is not. This s is from here, right? S squared over s is just s, so I pulled it all out. And then use the minus 2 is up here as well. So now I think I'm going to do the same thing I did in the previous integral, which is just make this into 4 different fractions. And then we can say this one goes here and this one goes onto the top here, which is, I think, what I've done here. And then there's a whole bunch of cancelling, as we've seen before. 2a plus 2 minus a is just a plus 2, I guess. But then we've got a minus 2 there, so that's just an a. And then what have I done here? I've put the C and the K back in. And I think that's about it. I think everything else is pretty much as it is. So that's going to be there, I guess. And so now we know that the density function of t is just this. It's the thing in the integral, right? It's the f of x in the integral, or f of u in the integral. So it's just this, I guess. Okay, so we're on the home straight now. Hence show the product of the median time and the median speed. So median time is the median for this, I guess. Or yeah, sure. And the median speed is for is the one that we found earlier because the speed is about v, right? And likewise, the expected value of v we found earlier, and we don't know the expected value for t yet. So okay, what we need to do, it says hence, so we need to use what we just figured out somehow. When we look at this density function and look at this density function, they look kind of similar. And we can actually change this one to be basically exactly the same as this one if we just do some work here. If we write this on the bottom, so this is a crazy way of doing it, but I think it just about holds. Minus a minus minus 2a is a, and minus 1 minus minus 2 is plus 1. So this is, I haven't done anything else or anything. This just about holds. The reason I did this is because this is essentially a k to the minus 1, 2a plus 2 times. So that's a 1 over k, 2a plus 2 times, which means I have exactly enough 1 over k's to put it in this bracket and write this bracket as s over k plus u, 2a plus 2 times. And I can also do the same sort of thing up here where I pull out a minus 1. And the reason I'm going to do that is because I can now say that, well, okay, this denominator is even better now. It's just that k is now acting as s over k. Can I do the same with the numerator? Well, this is just k a plus 1 times flipped over. So if I times it with this one, it makes s over k a plus 1 times. And now this is perfect, right? It looks exactly the same as this, where k has been replaced with an s over k. Which means that, because those are just constants, right? It means that the median of the t thing is the same as the median for the other thing, except k gets replaced with s over k. So the median for t is s over k, and likewise the expected value of t, just replace that k with an s over k, is this thing here. And so then when I do the product of the median time and median speed, so product of the two medians is s over k times k, which is obviously just s, which is what they wanted me to get. And the product of the expected time and the expected speed is going to be this times this. Bit more work to do here, but the k's cancel, and then we end up with a bunch of squares. Now, a plus 1 squared over a squared is definitely bigger than 1 for all a, right? Because this numerator is ever slightly bigger. For any a, this numerator is just a bit bigger than this denominator, so therefore the fraction is bigger than 1. And therefore this whole thing is s times something a bit bigger than 1, which means it's a bit bigger than s, and that's what they wanted me to get as well. Thanks for watching, and that's the step 3 stats booklet done.